Good evening. Welcome to the California Colloquium on Water. Tonight we have a great lecture for you. My name is Linda Vita. I'm the director of the Water Resources Center Archives, and we're the major sponsor of the lecture series. Of course, along with the Faculty Advisory Committee that helps pick the speakers and the sponsorship that we get from deans across campus. A few quick announcements. If you are in Matt Condolf's seminar class, we need you to sign the sign-up sheet that is in the back of this room. Please just indicate in the affiliation column that you are part of Matt's class. Also, a reminder that if you are not currently receiving a reminder email about the Colloquium series, please sign that same list and we will add you to our email list. And we videotape each lecture so that if you know someone who has missed a lecture, we post them to the website about 2 weeks afterwards. And then I would like to make an exciting announcement that starting this semester, the Water Resources Center Archives is going to sponsor one UC Berkeley graduate student to go on a Water Education Foundation tour. And we're still drawing up the guidelines, but the idea is that in the fall semester, the student that is selected will be able to go on a tour in the spring. And their 2009 schedule of tours just came out, and I have some brochures in the back. So we will plan to advertise this widely. So in the next couple of weeks, please look for the announcement. And basically, it's going to be a raffle. So you're going to submit your name, and we're going to pick a name out of a hat, and that's how we're going to pick the winner. So with that, I'd like to introduce Professor Narasimhan, who will introduce our speaker.
Good evening. It is my great pleasure today to introduce today's speaker. We have structured this colloquium series in a manner that it will integrate the entire campus, so that the 4 speakers that we invite each semester, we have one from science, one from engineering, one from social sciences, and one from the humanities. That is how we try to look for speakers. So today's speaker is from the science side. He is a geologist and a natural scientist. So he'll give today's presentation as part of the science discipline. Dr. Mario Sophocleous is from the Kansas Geological Survey located at Lawrence. It turns out that Kansas Geological Survey is also part of the University of Kansas, so it is very academically linked. I know Marius from his days as a student back in the late 70s at the University of Alberta in Edmonton. And since then, our interests have continued. And lately, he has spent a lot of time thinking about sustainable groundwater management in Kansas. And there is a lot of experience that has been accumulated in Kansas, which he's going to talk about today. In fact, when I invited him to speak, I thought he could talk about groundwater experience from the entire Midwest. But Marius is so modest, he said, I don't know I can handle everything else, but I will talk about Kansas. I said, we'll take it. And so here, before I asked Marius to come here, I have here the president of Groundwater Resources Association of California, Jim Strandberg, who wants to honor Marius for his contributions in groundwater with something special. So after he honors Marius, he will start his talk. Jim?
Thank you very much. Let's see, can you hear me okay? Good. Well, good evening, everyone. My name is Jim Strandberg. I'm a hydrogeologist with Malcolm Perney, and I'm currently the president of the Groundwater Resources Association of California. That is a organization of some 1,400 scientists and engineers and planners and educators and others who are very interested in the groundwater resources of the state. And our mission is to help educate members in the field, the public, on protecting and improving the groundwater resource. And it's my pleasure to present to you, Marios, our California Groundwater Management book. This is a book that is a compilation of a great deal of information about groundwater within the state of California, and it was authored by a number of leaders within the field. And it is our pleasure and honor to present this to you this evening.
Thank you very much. I have my thing. Okay. Yeah, you can turn it off. Okay. Well, thank you. Thank you. So I'll leave this down here. Okay, thank you. And good evening. First, I would like to thank Professor Narasimhan for inviting me to come here, and I'm very pleased to be here. You hear me all right? Okay. Very few areas of public policy are as contentious as the issues surrounding management of our environment and natural resources, particularly water. Sustainable development has emerged during the late 1980s as a unifying approach to concerns over the environment, economic development, and the quality of life. The World Commission on Environment and Development, better known as the Brundtland Commission, defines sustainable development as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. This intergenerational perspective implies that we must use the water resources in ways that are compatible with maintaining them for future generations, thus constraining our management of water. Despite the progress that has been made in defining the goals of sustainable development, the mechanisms to bring about these changes are not clear-cut and are still a matter of debate. The challenge we face is to turn the principles of sustainable development into achievable policies that lead to concrete change. The move from principle to practice is far from easy and poses a series of dilemmas for which there are no clear solutions. Although science can assist by exploring the implications of different interpretations of sustainability, science cannot say that one particular interpretation is the code correct and code one for society. But sustainable solutions will have to be based on fundamentally sound hydrologic analysis and appropriate technologies. In this presentation, I will emphasize the hydroecological underpinnings of sustainable development. First, I will talk about the sustainability concept of safe yield and point out some of its shortcomings as a basis for developing groundwater planning policies. And I will give two short examples of groundwater systems and their responses to development. Then I will briefly expand into the more general concept of sustainability from the hydroecological systems perspective and outline our still evolving ideas on environmental sustainability. I will subsequently expand on the path Kansas has taken towards achieving water sustainability and conclude with suggestions to move forward in the water sustainability domain. Okay, to protect groundwater supplies from overexploitation, State and local agencies in Kansas and other states and countries enacted regulations and laws based on the sustainability concept of safe yield. Safe yield is commonly defined as the attainment and maintenance of a long-term balance between the amount of groundwater withdrawn annually and the annual amount of recharge. Therefore, safe yield only allows water users to pump no more groundwater than is replenished naturally through precipitation and surface water seepage, generally known as natural recharge. But under natural or equilibrium conditions, recharge to an aquifer results in an equal amount of water over the long term that is discharged out of the aquifer into streams, springs, or seep, as shown in the upper figure of this slide. Consequently, if pumping equals recharge, streams, marshes, and springs may eventually dry up, as you see in the lower figure. Continued pumping in excess of recharge may eventually deplete the aquifer. This has happened in several locations all over the world. Probably the best known example in the US is the Ocala or High Plains aquifer, shown here. And here is a closer up view of the High Plains aquifer, where declines of more than 30 meters over a 30-year period were common in parts of Texas, New Mexico, Oklahoma, and Kansas, as you see by the red colors in the slide. Focusing on Kansas, we see that some areas in western Kansas have been depleted by more than 50% of their saturated thickness, as indicated by the red colors in the slide. Maps comparing the perennial streams in Kansas in the 60s, as shown in the upper slide, to those in the 90s, shown in the lower slide, show a marked decrease in kilometers of stream flow in the western third of the state. To understand why this is happening, a thorough knowledge of the hydrologic principles concisely stated by Charles Tice back in 1940 is required. Under natural conditions, prior to development by wells, aquifers approach a state of dynamic equilibrium. Discharge from wells upsets this equilibrium by producing a loss from aquifer storage. A new state of dynamic equilibrium is approached when there is no further loss from storage. This is accomplished by an increase in recharge, a decrease in natural discharge, or a combination of the two. An increase in recharge can occur by inducing recharge from stream water or any other surface water body when, for example, the cone of depression in the groundwater level surface caused by pumping wells has reached that surface water body. Thus, groundwater sources include groundwater or aquifer storage and induced recharge of surface water. The timing of the change from aquifer storage, depletion, or mining to induce recharge of surface water bodies is key to developing water use policy. The shape of the transition or growth curve for an idealized radial uniform aquifer is shown in this slide in normalized form based on Glover's analytical solution, where the percent of groundwater withdrawal derived from aquifer storage is plotted on the y-axis against dimensionless or normalized time on the x-axis. This graph shows that during the early times since pumping started, almost all of groundwater pumped comes from aquifer storage. As time passes, an increasing percentage of groundwater pumped comes from induced recharge of surface water. Since the 1980s, three-dimensional numerical models of the complete stream aquifer hydrogeologic system have been used for water rights and for water rights and other purposes. These models provide a predictive tool explaining the connection between well-field withdrawal and surface water depletion at particular sites. Groundwater models are capable of generating the transition curve for any case by simulating the management of or policy alternatives in terms of the sources of water from groundwater storage and from surface water depletion throughout the area of response. What is employed in the model for such projections are 1, specified withdrawal rates, 2, well distribution, and 3, drawdown of water levels to an economic or physical limit. However, a planning horizon must be defined to assess which phase of the transition curve will apply during the period of the management plan. Stan Lohman of the US Geological Survey in the early 70s discussed safe yield and the sources of water derived from well fields using a series of 5 example aquifer types. His conceptual model was extended in the late 80s to illustrate quantitatively the rate of change of water sources in the types of systems that Lohman discussed. The 3-dimensional aquifer model ModFlow was used to calculate the drawdown and depletion rates for the example systems that Lohman described. Here I will briefly present only 2 aquifer types. One, a valley of a large perennial stream in a humid region, shown in the upper slide, and a valley of an ephemeral stream in a semi-arid region, shown in the lower slide. In each case, a well field was specified to produce at practical rates from each system. Withdrawal was simulated at a constant rate. Generally, the surface water sources were simulated and as an amount of water available to be captured from perennial streams, springs, or from reduction of evapotranspiration. The calculated curves shown on the right-hand side of this slide display the transition from full reliance on aquifer storage to full reliance on induced recharge of surface waters for the 2 aquifer types considered. The shape of the curves is generally reminiscent of the transition or growth curve for a radial flow system we showed earlier. These curves show the importance of selecting a suitable planning horizon when evaluating the effect of groundwater withdrawal. The phase during which almost all of the withdrawal are derived from induced recharge from surface water ranges from about 4 years in the case of a perennial stream in a humid region to approximately 375 years in the case of the semi-arid area, as shown here. The results suggest that a groundwater policy based on equilibrium conditions or on a mining strategy should be thoroughly examined for its physical and economic effects through the years. Both arid and humid regions may require this type of information before the effects of a water plan are fully understood. Over the past several decades, the concepts underlying management of water resources have gradually shifted from a deterministic worldview based on the balance of nature to the recognition that nature is characterized by chance and randomness, that natural systems are inherently variable, patchy, and complex. This realization dictates, first, management in the context of the ecosystem, that is taking a holistic approach rather than managing parts as though they were in isolation. And secondly, use of an adaptive management scheme that is responsive to changing environmental conditions. So the next level of sustainable yield addresses the sustainability of the system, not just the fish, but the marine food chain, not just the trees, but the whole forest, not just the groundwater, but the running streams, wetlands, and all the plants and animals that depend on them. A worthwhile approach, but fraught with difficulty. We cannot use a natural system without altering it. And the more intensive the use, the greater the alteration. How much is too much? What are the central characteristics that must be preserved or sustained? Is there any way to answer these questions before it is too late? Here is the forefront of the sustainability problem. The evidence shows that we have altered the hydrologic cycle as well as the cycles of most elements, that we are altering climate, and that biodiversity is declining rapidly. These events call for a more holistic concept of system management that has the goal of maintaining and restoring the ecological integrity of the resource rather than simply preserving water quantity and quality. The need to manage groundwater resources as an integral part of the overall available water resources is better understood today by scientific experts and water resources managers. Integrated resource planning has relatively recently emerged as a tool of total water management, assuring that water resources are managed for the greatest good of people and the environment, and that all segments of society have a voice in the process. This concept of enlightened management is now taking hold in Kansas and other states as well as other countries. In response to persistent groundwater level declines, especially in western Kansas, the Kansas legislature back in the early 70s passed the Kansas Groundwater Act, authorizing the formation of local groundwater management districts, or GMDs as we call them, to help control and direct the development and use of groundwater resources. Since passage of that enabling act, 5 districts have been formed, as you see in the slide, of which the 3 western districts, 1, 3, and 4, overlay all or parts of the Ogallala Aquifer proper. These 3 western districts have the greatest number of large capacity wells and the highest rate of water level declines, in addition to having the least precipitation, being under a semi-arid climate, and least groundwater recharge. We are talking about in the order of 10 millimeters a year here. Because recharge rates are so low in western Kansas, so-called safe yield policies in which groundwater withdrawals are restricted to average recharge rates have not been adopted as being too harmful to the region's economy. Thus, each of these districts has employed a plan known as planned depletion policy, which allows a part of the aquifer to be depleted up to 40% over a period of 25 years. However, these western Kansas districts recognize that their long-term goal is to reduce the rate of water use in order to prolong the life of the aquifer and to assure future economic stability in the region. Towards this end, the Northwest Kansas Groundwater Management District number 4, shown here in green, implemented a so-called zero depletion policy in the early 1990s. This zero depletion policy limits the pumping of water from an aquifer for new wells so as not to exceed the estimated average amount of natural recharge. As a result, very few water rights are being approved under this regulation. The districts to the east, that is GMDs 2 and 5, shown here in bluish colors, which have more precipitation and thus more groundwater recharge, initially adopted a so-called safe yield management plan to balance groundwater pumping with the average annual recharge. Under this policy, shown in this slide, the total appropriation in a 3.2 kilometer radius circle or 2-mile circle around a proposed irrigation well, shown here in red, were limited to the long-term average annual recharge calculated for that circle. Thus, if the quantity already appropriated in that 2-mile circle, as indicated by these blue circles, plus the quantity proposed under this application, this new application, if that total amount does not exceed the long-term average annual recharge, and if some spacing requirements are satisfied, then a water appropriation permit is granted. Otherwise, it is rejected. However, although this safe yield policy has slowed down the rate of groundwater decline, it has not stopped groundwater declines. Both GMDs 2 and 5, shown again here in golden colors, experienced groundwater level declines of more than 10 meters in parts of their districts since establishment of this safe yield policy. In addition, as a result of these groundwater level declines, stream flows in western Kansas and central Kansas streams and related aquatic and riparian ecosystems have been in decline, especially since the mid-1970s. The upper part of this slide shows a graph of median annual stream flow of the Arkansas River, shown in the lower panel, based on daily stream flow records for Garden City, Dodge City, Kingsley, and Great Bend for the period from 1950 to 2006 in this slide. The pattern in reduction in surface water discharge, especially since the mid-1970s, is clearly visible. The situation on the ground for Dodge City, Kingsley, and Larned, which is somewhere between Kingsley and Great Bend, is shown in the next couple, 3 slides I'm going to show you, as seen today. Here is the Ark River at Dodge City. Here it is at Kingsley. And here it is at Larned, between Kingsley and Great Bend. Agricultural conservation practices also contributed to runoff reduction to streams. Declines in stream flow also exert a direct impact on surface water quality by reducing the dilution base available to effluents from sewage treatment plants and other pollution sources. In response to these stream flow declines, the Kansas legislature passed the minimum in-stream flow law in the mid-1980s, which requires that minimum desirable stream flows be maintained in different streams in Kansas. The state has also established total maximum daily load limits, or TMDL limits, in selected streams in Kansas in the late 1990s in an attempt to curb down on the dwindling water quality problem and protect aquatic ecosystems. As you know, TMDL is a calculation of the maximum amount of a pollutant that a water body can receive and still meet water quality standards, and an allocation of that amount to the pollutant sources. As a result of the failure of the so-called safe yield policies of the Kansas GMDs to prevent declines in groundwater levels and stream flow, GMDs 2 and 5, shown here again in golden colors, moved towards conjunctive stream aquifer management by amending their safe yield regulations to include base flow that is the natural groundwater discharge to a stream, as groundwater appropriations or natural withdrawals, along with regular water permit appropriations when evaluating a groundwater permit application. Base flow is estimated as the stream flow that is exceeded 90% of the time on a monthly basis as a measure of dry weather flow. The concept shown in this slide is to prorate the base flow to a series of phantom wells known as base flow or stream nodes, shown here as small blue dots along the stream center line, spaced 400 meters or a quarter miles at quarter mile intervals, which is the GMD's well spacing requirement, each having an annual quantity of water assigned to it equal to its pro rata share of the estimated base flow, which is considered its appropriation for 2-mile circle computations. If there are such nodes in a standard 2-mile circle from the proposed well to be permitted, they are each treated as water rights for purposes of determining whether or not a new application should be approved. The state regulatory agencies and the GMDs realize that the problems of controlling groundwater depletion is complex, involving not only hydrogeologic, but also socioeconomic and legal considerations. The Division of Water Resources, or DWR, which is the state's, meaning Kansas State's, water rights regulatory agency, and the GMDs adopted a suite of management programs involving controls on new development, regulation of existing development, well spacing requirements, annual water use reporting, water metering, water supply augmentation programs, including water conservation measures, water use efficiency schemes, artificial recharge structures, participation of the Western districts in an active weather modification program, participation in recently proposed water banking schemes and other programs, as well as public education and involvement programs. The DWR and the Kansas Water Office, which is the Kansas State's water planning agency, have also initiated a comprehensive basin-wide management program in areas of Kansas with significant water problems. Holistic and proactive approaches are integral parts of this program, as well as close consultation and cooperation with the local districts, irrigators, and other interested parties. The Kansas Geological Survey assisted in the program's advancement by developing and applying integrated watershed and groundwater models. However, an accounting for such modeling is beyond my presentation, beyond the scope of my presentation today. The approach taken by DWR and the basin working groups was that of incentive-based alternatives to affect change in target problem areas within the basin. The city of Wichita, Kansas, let me see. Oh, here it is. Yeah. The city of Wichita, Kansas, shown here in pink in the lower slide, has also developed an innovative integrated resource planning program which includes both conventional and non-conventional local water supplies to meet projected demands, such as capturing excess flow river water and riverbank storage water from the Little Arkansas River on an as available basis. This water is being recharged and stored in the Equispeds aquifer just north of Wichita, shown in blue in this lower slide, to be recovered in times of drought. The plan established a priority of water use whereby water that would normally flow through the area would be used first, saving slowly replenished water resources for times when the first priority water is not available. The progressive evolution of Kansas water management, which incorporates local groundwater management districts and their management programs, minimum stream flow and TMDL standards, the use of with the water use reporting and water metering programs, the use of modified safe yield policies in some districts, the DWR sub-basin water resources management program, and the integrated resource planning by the city of Wichita, as well as other programs, are all appropriate steps, although still more are needed towards the attainment of sustainable development. In the past, the volume of recharge to an aquifer was accepted as the quantity of water that could be removed from an aquifer on a sustainable basis, the so-called safe yield. We now understand that the sustainable yield of an aquifer must be considerably less than recharge if adequate amounts of water are to be available to sustain both the quantity and quality of streams, springs, wetlands, and groundwater-dependent ecosystems, or GDEs. Quantifying what these environmental provisions are and what the non-market values of these ecological assets are constitute urgent areas of research needs. Groundwater management responses in areas of over-extraction must include bringing use back to sustainable or at least community acceptable levels when exploring more, while exploring more sustainable options. Wise management of water resources needs to be approached not only from the viewpoint of focusing on the volume of water available for sustainable use, but also from the impact of groundwater exploitation on the natural environment. Streams, wetlands, springs, groundwater-fed lakes all depend on the depth to the water table, not necessarily on the volumetric amount of groundwater available. Because of their interdependence, groundwater resources cannot be managed separately from surface water. Also, because of uncertainties and spatiotemporal variabilities of key controlling variables such as recharge and other hydrologic budget components, sustainability assessment should be understood as a dynamic and iterative process requiring continued monitoring, analysis, prioritization, and revision. Given such large uncertainties, it is imperative to select policies that are precautionary. That is, policies that do not take unnecessary risks with sustainability and do not count on unrealistic technological fixes for their success. Local decision-making is considered the preferred route to water management, as is indicated by the establishment of local groundwater management districts in Kansas and elsewhere. Because local conditions vary significantly within the U.S. High Plains region and elsewhere, environmental differences affect water availability and use. Detailed water management plans will necessarily be sub-regional to adequately adjust to local conditions. Traditional approaches to estimating future water needs and then developing new water supply sources and treatment facilities to meet these needs will no longer be adequate. Doing more with less by increasing the productivity of water through investments in conservation, efficiency, recycling, and reuse is the way forward. Water marketing, regional water sharing networks, and water banking are some of the more recent creative planning approaches to satisfy future needs. Due to the fact that Groundwater is in most situations a common property resource dependent on the actions of many users. Its in situ value to individuals is relatively low. In addition, the impact of one individual on the aquifer may not be generally discernible in terms of the aquifer as a whole, although the aggregate impact of a large number of groundwater users and polluters is usually easily detectable. A major challenge is to assure each individual that others are behaving in ways that protect the resource base, and to communicate with the multitude of diverse groundwater users to encourage sustainable use of the resource base. The solution of regional and local water problems requires education, technical assistance, and supporting research. It is imperative that the community at large participates in policy formulations and in judgments of what is to be sustained. Strong public education and outreach programs, as we also are attempting to do in Kansas, are always needed to improve understanding of the nature, complexity, and diversity of groundwater resources, and to emphasize how this understanding must form the basis for operating conditions and constraints. This is the only way to positively influence, for the long term, the attitudes of the various stakeholders involved. Pressure from the community, including you, the audience, for better management of our natural resources will be the main driving force for most changes. And finally, a few additional words on the steps we need on the steps we need to follow to face up to this sustainability challenge. Sustainable use of groundwater must ensure not only that the future resource is not threatened by overuse and depletion, but also that natural environments that depend on the resource, such as stream flows, riparian vegetation, aquatic ecosystems, and wetlands, are protected. To properly manage groundwater resources, managers need accurate information about the inputs, i.e. recharge, and outputs, i.e. pumpage and natural discharge, within each groundwater system, so that the long-term behavior of the aquifer and its sustainable yield can be estimated or reassessed. A first step towards this mass balance exercise is a compilation and synthesis of all major hydrologic studies conducted in the area of interest, such as the one we have recently completed in Kansas, as shown here. The people of Kansas, and also elsewhere, through their citizen committees, their local and state agencies, and their governors, are unanimous in their desire to extend and conserve the life of the Ogallala aquifer. For example, the Kansas Water Plan objectives call for a reduction in water level decline rates within the Ogallala aquifer by 2010, which is in a couple of years, and implementation of enhanced water management in targeted areas known as aquifer subunits, as well as additional goals, as you see here. In the long term, it is impossible to extract more water from an aquifer than is recharged to it by seepage from precipitation and surface water bodies. Sooner or later, the pumping rate will automatically have to adjust to the availability of water. Clearly, it is wiser to strike this balance at high groundwater levels than at low levels, to provide leeway for temporal overdraft and therefore supply safety, and also because the cost of pumping increases as water levels decline. The key steps to move towards sustainable use of groundwater are basic and common sense from a hydrologic perspective, but highly complex from a socio-economic, legal, and political perspective. A sustainable groundwater management strategy can only be as good as its potential for implementation. Improve the knowledge base, the reporting and access to information, public education, and understanding of the public's attitudinal motivations, and further improve water efficiency and crop productivity. Embrace the ecosystem and adaptive management approaches to manage groundwater. In this regard, the most important element of adaptive management is the capacity to initiate and maintain long-term monitoring programs. The capacity to adjust management actions in response to monitoring is essential to achieving sustainability of the resource. Exploit the food potential of rain-fed or dryland agriculture, as well as biosaline agriculture wherever brackish or saline water resources and soils are plentiful, such as in many parts of Kansas, by the way, in order to relieve considerable pressure on irrigated agriculture and on water resources in general. And finally, adopt a goal of sustainable use, fostering the long-term perspective to the management of groundwater resources is a most important attribute to the concept of sustainability, as there may be circumstances that warrant temporary overpumping of an aquifer that could be balanced, for example, by intervening additions of groundwater storage, and also allow time for transition and readjustment to a diminished groundwater availability. And here I will stop and see if we could have some discussion. Thank you. Yes.
Do you have the capability, or can you force groundwater pumpers to provide information? I mean, one is, can you quantify individual pumpage, and can you require individual pumpers to disclose their annual pumpage?
I was asked to repeat the questions, so I'm going to repeat your question. If we have a means of figuring out how much is being pumped, and if we have the capability of reducing this pumping. Both are good questions. And I would like to say that Kansas is a pioneer in water use reporting. In other words, we have a program in place that every irrigator has to file in a water use report at the end of each year. If he doesn't file that report, he's subject to a fine up to $250. So we get 99% compliance plus. So we have an excellent water use reporting system, and we have very good data on water use in Kansas. And we publish this every year. Now, with regard to if we have the power to cut down groundwater use, this is a very touchy and sensitive issue. And we have, in Kansas, we have the prior appropriation doctrine, which means that once you get a permit to irrigate a certain amount, it's almost you have that in perpetuity. And nobody can, and it's like a quote unquote property right. And it's very difficult to change it. However, in Kansas, we have, first of all, in Kansas, the water is dedicated to the people of Kansas. So even if we say it's a private property, it's within some limits. Now, in Kansas, we have special regulations that the chief engineer of the state, which is the water czar of the state, can declare an area as an intensive groundwater use area. It's called IGUGA, the initials of that. And once he declares an area as an IGUGA area, then a public hearing is called. So everybody comes in and they say what they have to say, they explain what the problem is, and the chief engineer, after this discussion, the chief engineer has the power to reduce their water rights. So this happened actually in central Kansas. We have a wet walnut creek valley which supplies a well-known wetland, the Cheyenne Bottoms wetland. If some people heard of it, is one main central place on the flyway of the birds from North America to South America. And that place, that Cheyenne Bottoms area, was running out of water because all the streams which were feeding into it were drying out. And they had an intensive groundwater use control area in that area, and they reduced all the pumpers or irrigators more or less equally, more the juniors, but also the seniors by a certain percent. Yes. Yes.
I have a follow-up on what you said, and then also a similar question on groundwater. Speak up. Okay. I thought you could repeat my question, so I have a follow-up on what you just said.
Yes.
I have another question. So the follow-up question is, how do you know that they're filling in these water use reports accurately? So they may be lying or not lying. And my second question is, how easy was it to implement this system of groundwater monitoring on a statewide basis?
Okay, good questions. The questions were is, how do we know that the water use reporting is accurate? One. And two, how do we monitor groundwater on a statewide basis?
How did that system get started, implemented?
How did that system get started?
Well, it wasn't, in California we don't have that system. So it's a
Okay,
question
in Kansas we have a very good system of groundwater monitoring, and it's good to emulate it, I think. Okay, now how do we know that water use reporting is accurate? We have several things we check. One is we have a number of people dedicated to going and checking. Now, by the way, first, before I say this, is that in Kansas now, all wells are metered. They have meters, certified meters by the local groundwater management districts. So we have a group of people who go and randomly measure, check these meters, so they compare that against what they report. But also we know what is the average water use, more or less, so many acre feet per acre for every climatic subregion of the states. So we have an idea how much the farmers need to irrigate. So if something is way beyond the limits, we go check. So this way, we check. Now, How did the groundwater monitoring system started? We started many years ago when I first came to the survey, to the Kansas Geological Survey. We were cooperating at that time with the U.S. Geological Survey. Do you have anybody from the USGS here? If I say something, they may not get offended. But as we were, every year that program we had with the USGS used to be increasing in cost. The wells kept increasing every year. The cost kept increasing every year. So in the 80s and early 90s, we did a geostatistical analysis of the monitoring system to find out which is the optimal size of a network we need to have in order to get the information with a certain uncertainty. So after doing this study, we found out that we need one well every 4 miles on average, let's say, to be monitoring to get our system in place. So we started reducing our network. It reached close to 2,000 wells a year. Now we have about 1,400 wells we monitor. And now we have, actually they invited me to go to China to explain to them how we monitor our aquifer. And we have an excellent system, if I may say so, of groundwater monitoring in the state. We automated the system so that all the monitoring wells are any kind of wells, irrigation wells, municipal wells, domestic wells, windmills, monitoring specially designed wells, etc. All these wells are put into a computer database with GPS things. So, and now we optimize the routes. We measure them every winter when there is not much irrigation. And we go there, and everybody now has their computer in their car, and as you go, it tells you the way how to reach the well. As soon as you reach the well, you see a picture of the well, so you identify it so you don't measure something else. And immediately the database shows you 10 years worth of previous records of that well, so you can compare your measurement, things like that. All these data are put in a minimum time, in a few days after that, after we check them, into the web, and they are publicly accessible to everybody. And now we also have these Palm computers. You take them out to the field, you don't need to have these other things, and everything is digitally entered. We have tables, we have things, everything go in, and you can go into our database, you can take a look at it, and our database is another marvelous thing. Helps you could choose what data you want, you can display them, you could make graphs automatically, you could put GIS maps and put whatever coverages you want, the streams, the county boundaries, whatever you want, it's all there. So you can visit the Wizard database. If you look at the Kansas Geological Survey webpage, you'll see. Yes?
That's not what I was asking.
Say that again?
That's not what I was asking. I was asking,
Okay.
how did you get started where there was no well monitoring and there was no meters on the wells? How did that process work?
Okay. Well, we had to fight a lot. When I first came to the survey, we didn't have this metering program, first of all. And of course, the farmers initially were very resistant to having their wells metered. But it takes patience and time and education. And everybody sees that for years and years we see groundwater levels going downhill. We need to do something. If you don't know how much you're pumping, how are you going to manage? So that's one thing with regard to water use, how we started on that. Now, with regard to the monitoring system, we always had a kind of a monitoring, but we improved it over time. Yes? Yes?
Two questions. So on that last question, were the farmers forced to pay for I assume these are totalizing meters that you have on there, or are you looking at their power records?
Well, they get some subsidization. I think they pay something, but they get some tax breaks or some other kind of incentives to put that thing.
And the second question is I assume you're running groundwater models. Are your groundwater models then integrated with your data management system so you can make forecasts and that sort of thing? And what models do you use?
Well, now, not before, but now the question was if our groundwater models are integrated with the monitoring, you say. Now, yes, in the sense that the last several modeling projects we have, of course, for all our modeling projects, we take advantage of our databases we have and of the data we collect. And the water levels we have is not only theoretical just to know the water levels. These water levels are actually used by the local groundwater management districts in their management plans. The management plan says that they have to figure out what is the saturated thickness under any well, or so based on this monitoring system we have, we make maps for them every year on a section by section basis, on a square mile thing. They have data on what the water level is on that section, what is the base of the aquifer at that, what is the saturated thickness of that thing. And based on these trends, we made projections. If you keep the same declining trend you had the last decade, in the next decade, let's say, we made just projections, simple projections that and we put them on a GIS map, which shows the expected life of the aquifer on a section by section basis, basically. So, and we put these maps up, and you see all these red colors. Red colors mean you have 25 years or less for that region. The others may have 50 years, others may have 100 years. Others are already depleted. So, and that was a real eye-opener for the people there. Yes?
I want to make two comments. One is that it's very interesting that this oblal aquifer system mostly behaves like an unconfined aquifer.
Yes.
It's directly connected to the...
Yeah.
So the curve, that depletion curve you showed, is like an
Right.
unconfined aquifer. The early time is some elastic storage.
Right.
The late time is all desaturation. That's very interesting. But we also have, in other parts of this country, deeper aquifer system, which is more confined. And their extraction rates are somewhat different. Just a matter of detail that in this we are going to have.
Right.
all kinds of
Right.
systems.
That's correct.
But from the point of view of managing an unconfined system which directly communicates with the streams and wetlands and so forth, this is a very outstanding study. It gives us a lot of insight.
Yes.
The second comment I want to make is that on the one hand, there is a lot of litigation, especially in California, which groundwater rights are held as sacred and don't want to be interrupted, although it is intimately connected with surface water. So we have public trust applying to surface water, but not to groundwater, so we have a management situation which is pretty bad. But the Cheyenne bottom wetland example you showed is very interesting, that although, quote, some of them, even in Kansas, think that there is a perpetual right to have this quantity of water and so forth. Ultimately, when really water levels go down, there's a mechanism by which everybody comes together and say, we have to share this responsibility.
That's right.
Give back some of our rights. So sooner or later it's going to happen. And we are seeing that in Colorado, for example. In the South Platte Basin, 4,000 wells have been shut down permanently.
That's correct. And with regard to your earlier comment, I like to say that what I talked today I talked only about the high plains, but we also have deeper aquifers like the Dakota aquifer, which are confined, the Ozark aquifer, which is Camber Ordovician, and we identify those, and we, in our analysis, we separate them, and we have separate management schemes for these confined aquifers, because the spacing, for example, of wells could be much larger for the confined aquifers because of the change. But in Kansas, the Ogallala aquifer is behaving as a regionally unconfined system. And of course, people don't like to be managed wholesale, like they want only to pay attention to where the biggest decline is, only in that smaller area, not everywhere. So we decided, people decided they prefer aquifer subunit so-called management. Now for that we need also special monitoring. Now we are experimenting in expanding our monitoring system with so-called index wells. In other words, we go and put some wells in some specially designed monitoring well in an area, put some pressure transducer, use telemetry system, and we check to see how typical is that well compared to the surrounding wells. So we go and survey the surrounding wells as well, and we do that. We have special funding for a few of these index wells, and we are working on that right now for that. Because to manage subunits, you need more monitoring. Yes, sir, up there.
My question is, when you're establishing the base flow to try to give back
Yes.
from the river, what are you using to establish that? Because if the aquifer's already been partially depleted, where previously a stream may have been a gaining stream, it may now be a losing stream.
Good question. What do we, if we have large-scale development now, or whatever stream flow we had before now is diminishing, how are we going to calculate base flow on a diminished flow stream, for example? Well, we are lucky in Kansas because we have long time series records. This is the value of having long time series of records. And we go back to the flows in the 40s and 50s before development affected things, and we can calculate base flow from there. Yes?
As a follow-up to that, some people believe that the past 100 years or so have been exceptionally wet based upon historical climate record. So as we move into possibly hotter, drier years, how valuable do you think that data will be to adjust to predicting base flow as what it should be if we weren't pumping?
Well, knowing the future climate of your area, it's very useful. And in Kansas, I mean, we hear all these climate change scenarios for different areas, but in Kansas we don't have any specific study on long-term changes based on Kansas data. So we are in the process of collaborating with the USGS, has a new project, I think, on water availability on the high plains. And they say that they came over to talk to us, and we talked to them about what we have. And one good thing which might come out of it is that they are contracting also with the Boulder Climate Change Center there to use climatic data from the High Plains region to project what the future climate would be based on these climate change scenarios. So if we have, I think I told them that the most useful thing we could have with them if they could deliver on that. And so if we know that, then we would know with more definitively what the future holds. And if we see that it's more a dry scenario or a wet scenario or whatever, that would help us anticipate and plan a little better how to best manage whatever we have left. I'm not sure if I answer your question, but more or less. Yes, Vicky. Yeah.
Would you comment on other aspects of the monitoring program statewide, such as water quality, if there's any unconfined, confined monitoring of the system?
Now, I miss a part of your question in the middle. To comment on what you said?
On other components of the statewide monitoring system, such as water quality or subsidence?
Yes, right. We also have a water quality monitoring network. That is handled by another agency, not by us, the Kansas Geological Survey. It's handled by the Kansas Department of Health and Environment. And they go monitor quite a number of wells every year or every few years, I'm not 100% sure. And they produce reports and maps on how the water quality of the state's waters is changing. And also they are monitoring stream water quality as well, and lakes, etc. What other aspect? Subsidence. Well, we are kind of maybe lucky in Kansas. Despite these big declines, we haven't noticed visibly any major settlement. The only problem we have is sinkholes in some very localized areas. and that is attributed to salt dissolution at depth. But, however, I wanted to try this insert thing, but it's too expensive, and we need some funding agency to give us some money to take a look and see if the settlement, we see some settlement, but it's in the order of millimeters or centimeters, and we don't notice it. But of course, the High Plains aquifer is mostly sand and gravel aquifer with indurated layers in between. Of course, there are lots of clays as well, but not a regional uniform, thick clay layers to be dewatered and be settling like in other places, like you have in the Central Valley, maybe here. Yes, Vicky. Linda. Sorry.
Just a question. You mentioned that. I mean, it sounds like Kansas is, very far ahead in their water, in the groundwater monitoring, et cetera. Are there any other states that are adopting this?
Well, actually, I'm in the process of completing a review and survey of all the High Plains states, of what their rules and regulations and their management practices are. And different states have different systems and different procedures, but eventually all of them very gradually, I think, are moving to the realization that we have one resource and the rules and regulations need to follow the science. Like in Texas, they still have this rule of capture thing, like which means that the owner of the land has absolute right to pump as much as he or she wants, irrespective of the neighbor. But of course, gradually, like in Texas, they bring some other schemes to modulate this rule, which they cannot change legally, but they put these local management districts or management areas, they call them, and the people there could put their own regulations on how to do that. Or in some cases, like in Edwards Aquifer, they, because of the importance of those springs and the springs ecosystems, they devise some special rules for that, and they overridden this other absolute ownership of ideas they had. And different states, I noticed they have some particular things which I think are innovative and good ideas. So I'm trying to bring all this together so people could see some examples to emulate from different states eventually.
One more question. Just a quick one. So,
Yes.
The conventional wisdom is it the Ogallala or Ogallala? I always get it wrong. Is it Ogallala?
Ogallala?
Is the conventional wisdom is the Ogallala is not sustainably managed, or not, it's not the
That's correct.
That's conventional wisdom. So can you update us as to what's going on over either just the Kansas part of the aquifer or all of the aquifer? Is it still not sustainable in Texas or in Kansas? Is it sustainable?
It's everywhere not sustainable except, the aquifer is predicted to decline everywhere except Nebraska. Nebraska has a lot of thick, saturated thicknesses of the High Plains. But in Texas, Oklahoma, New Mexico, and Kansas, it's a non-sustainable entity. as it is presently.
Is there any more questions?
You had one question there? Yes.
I mean, from where we are here in California, without any requirements to report groundwater extraction rates and not a statewide monitoring program the way you have, can you talk a little bit about the benefits of some of those programs that you have implemented in terms of maybe changed policies for land use planning relative to the resources that are available? How is the data being used to lessen overdraft in certain portions of the aquifer, or to improve stream flow in other areas that have seen declines in the past?
Well, as a result of our monitoring and documenting of the declines of streams, first of all, the legislature passed these minimum desirable stream flow standards, like quite a number of streams have to have a certain minimum flow. However, this was passed in the mid-1980s, which means they gave the streams water rights, so to speak, but their priority is mid-1980, which means that all the farmers before have more senior priority than the stream. As a result, our streams are still declining, despite this measure. Then later on, but the chief engineer has the authority to cut down irrigators if it is documented that the stream is depleting its flow because of the pumping. But it's a very difficult proposition because of the time lags involved. It's not like you pump now and you see instant result on the stream. That's a problem. So it's a very difficult thing to enforce. But then later they passed these TMDL standards, which also helps for the streams. But I think in the States, we are not yet as far advanced as some other countries like Australia and South Africa, and even the European Union lately, on how to enforce and maintain desirable, not necessarily minimum, stream flows or environmental flows in our streams. And this is an area we need to keep working at. Yes.
Thank you very much for this excellent, very educational talk. That's what this series is all about. I want to make one big comment. You said that, somebody asked a question. You said that other states are also slowly coming together, although each state is managing the water differently. And this is where the European Union becomes interesting. The European Union issued its Water Framework Directive 2000. And that is requiring all these 27 member countries.
They have to change their
to
laws.
come together, change the laws of water so that all
We cannot
countries
do
will
that
have
here.
the same philosophical basis.
Yes.
So the European Union gives a philosophical basis to manage water based on river basins with citizens' participation and so forth. And they say, now you change your laws and do it. And believe it or not, all the countries are now preparing the reports. The academies, the various academies are involved in it. It's really marvelous. But then what do you know? Europe is socialist, right?